Hello guys, in this video I'm going to be walking you through the applications of dimensional analysis. In the previous video we have looked at the dimensions of various physical quantities. Here we want to apply those dimensions. There are three areas of applications of dimensional analysis for this section. The first one is to check the consistency or homogeneity of equations. We can also use it to determine the units and dimensions of constants. There are some constants that are having dimensions, so we can use dimensional analysis to get their units and dimensions. We can also use it to derive equations. Most of the laws that we have in science, we can use dimensional analysis to derive their equations as well. So let's start with the first one, which is talking about the consistency of equations. We can use dimensional analysis to check whether an equation is consistent or not. An equation is dimensionally consistent if all the quantities have the same dimensions or units. For example, look at x plus y equals to z. If this is a mathematical equation, this equation will be dimensionally correct if the dimension and unit of x is the same as dimension and unit of y, is also the same as dimension and unit of z. Another example is v is equals to u plus 80. This equation will be dimensionally correct if the dimension of v is the same as dimension of u, the same as dimension of 80. It does not only apply to dimensions, the same thing for unit. If the unit of v is the same as unit of u, the same as unit of 80, then we say that the equation is dimensionally consistent. Now, let's take a look at principle of dimensional homogeneity, which helps to explain how an equation can be consistent. So, principle of dimensional homogeneity is what we have discussed in equation 1 and 2. It says that an equation is dimensionally consistent if all the variables have the same units and dimensions. Let's look at another example. S is equals to ut plus half at squared. This equation will be dimensionally consistent if the dimension and unit of s is same as dimension and unit of ut and dimension and unit of what? At squared. Now, there are two rules guiding this principle. The first one is what we have discussed, that for the principle to be obeyed or for an equation to be dimensionally consistent, all the terms must have the same units and dimensions. The second rule says that if there is a presence of trigonometric function, logarithmic function, trigonometric functions such as sine, cosine, or we have logarithmic functions, we have exponential functions. If we have exponential functions and equations that involve exponential, then their dimension must be equals to 1. That is, they must be dimensionless. For example, I have sine 80 over s. Sine 80 must be equals to 1. Means if we have a mathematical equation and the presence of sine, cosine, logarithm, exponential, their dimension must be equals to 1. That is, they must be dimensionless. And that is the main reason why if we have h is equals to u squared sine squared theta over 2g, dimension of sine squared theta must be equal to 1, so that the left hand side should be equals to the right hand side. Now let's look at examples under this application. The first example we want to consider is, look at these two examples that we are seeing on the screen. You can feel free to pause the video so as to try it. There are two methods of showing whether an equation is homogeneous or it is not. We have dimension method and base unit method. So I will use dimension method to solve the A part, then I will use the base unit to solve the B part. We can use any one depending on the one we are comfortable with. So now we have V square equals to U square plus 2AS. We want to show that this equation is dimensionally consistent. Since there are no trigonometric functions in this equation, so we need not to worry about that. We only need to deal with these three parameters. We have V square, U square, AS. To deal with this, let's obtain, since I'm using dimension method to solve this question, that means I need to obtain the dimensions of the parameters involved. Dimension of velocity, that's final velocity, is LT raised power minus 1, while the dimension of initial velocity is LT raised power minus 1. Dimension of acceleration is equals to LT raised power minus 2, while dimension of distance is equals to L. Now that we have gotten dimensions of the variables involved, let's substitute back into the equation. Anywhere I see final velocity, I'll replace it with LT raised power minus 1. So that will give me LT raised power minus 1 all square is equals to initial velocity, its own dimension is also LT raised power minus 1 all square, plus a pure number doesn't have dimension. It's only variables, letters that have dimension. So we ignore the two. These two that we are seeing, we ignore it. Then what dimension of acceleration is LT raised power minus 2, while dimension of distance is L. The knowledge of indices is important when dealing with applications of dimensional analysis. So we are going to use indices to solve this question. Let's quickly look at it. There's an indices law that says x, y raised power m simply means we're going to be having x raised power m multiplied by y raised power m. That means this m is a power that is meant for x and y variable. As we can see on the screen, the power of these two, this power is meant for L and T raised power minus 1. So the power for L here is 1, while the power of T is minus 1. So we are going to write by saying L, its own power is 1, that is 1 times 2, give us 2. T is its own power is minus 1, multiplied by the power that is outside, that give us minus 2. That gives us the same thing goes to this. We are having L square T raised power minus 2 plus L times L will give us L square T raised power minus 2. As you can see on the screen, the equation is dimensionally consistent since we have the same dimension on the left hand side and the same dimension on the right hand side. Then we can say that the principle of dimensional homogeneity is valid for this equation. Now let's look at the second example, which says that S is equal to VT squared plus 0.5 AT. We are using base unit method, so the unit of distance is meter, the unit of final velocity is meter per second, while the unit of time is seconds, and unit of acceleration is meter per second square, as well as this time is also seconds. Now that I have gotten the unit of the variables involved, let's substitute the equation. In this case, this is equation 2. We are going to be having distance is meter equals to velocity is meter per second, while time is seconds. We will have it to be squared plus, I've told you that pure numbers such as 0.5 don't have dimension, so dimensionless. In this case, we have acceleration to be meter per second square, while time is seconds. Now we can simplify this by using indices by saying meter is equals to meter per second. S becomes s square plus meter per second square multiplied by s. Now we have on the left hand side, we have meter is equals to meter. We have two s here, so let's try to simplify it. This s, let's try to simplify using indices, and that will give us s raised power minus 1 multiplied by s raised power 2. If I pick one of the s, because they're having the same base, then the first power is minus 1, while in indices multiplication means plus and second power is 2, so we are going to be having s raised power 1. So on the other side, on this first part of the right hand side, we have s raised power 1 plus meter. Let's simplify this as well. Let's simplify s raised power minus 2 and s raised power 1 because the power is 1. So we are going to have s minus 2 multiplied by s raised power 1. So we have s raised power minus 2 plus 1. Since they're having the same base, we apply indices as well. And we'll be having minus 2 plus 1 will give us minus 1. So in that case, our equation becomes s raised power minus 1. As you can see, the left hand side is meter, while the first part of the right hand side is meter per meter seconds, and the other part is meter per seconds. They are not having the same unit, so this equation is not dimensionally consistent. Therefore, it is not obeying the principle of dimensional homogeneity. Yeah, so in this second example, we can see that the equation is involving a sine function. So the first thing is to check whether this sine function is going to be dimensionless. So we start by, we can use base unit method and we can use dimension method. Prefer to use dimension method to solve this. You can feel free to pause the video to use base unit method as well. Acceleration dimension is lt raised power minus 2, while for time it is t, while for distance its own dimension is l. Let's check for that. Dimension of acceleration and dimension of t square over dimension of s give us dimension of acceleration is lt raised power minus 2 multiplied by the dimension of time is t, but we have it to be squared, over dimension of distance is l. So let's try to simplify this. You can see that l cancel l, then we'll be left with t raised power minus 2, t raised power 2. If I try to solve it using indices, I have t raised power minus 2, pick one of the t, since they have the same base. The first power is minus 2. In indices, multiplication means plus, then the second power is 2. That will give us t raised power minus 2 plus 2 give us 0. T raised power 0 will give us 1. That means this part is 1. In that case, the sine of at square over s, its own dimension is equal to 1. You can see that means the argument that sine function is equals to 1 is correct. Now let's go to check maybe the left hand side of the equation is equals to the right hand side of the equation, and that is the dimension of velocity is lt raised power minus 1, while the dimension of sine of the whole function, which is at square over s, it is equals to 1. So we can equate the two and say that lt raised power minus 1 is not equals to 1. Yeah, that means the dimension of the left hand side, which is velocity, is not equals to the dimension of the right hand side, which is sine of at square over s. That means the equation is not dimensionally homogeneous, and here the principle of dimensional homogeneity is not obeyed. The principle is not obeyed for this equation. That is all about the first application, which is used to check the consistency of an equation. Now let's look at the second application of dimensional analysis. Determination of units and dimensions of constants. We can use dimensional analysis to determine the units and dimensions of some constants in physics. There are some constants that have dimensions and units. Therefore, dimensional analysis can be used to obtain their units and dimensions. This application is actually based on the first application. That means we can obtain the units and dimensions of the constant provided that the equation is what? Dimensionally consistent. That means the left hand side is equal to the right hand side. Now, how are we going to go about this? Let me give you the steps that we can use to obtain the units and dimensions of these constants. So, for us to be able to determine the units and dimensions of the constant, these are the steps we are going to be making use of. The first thing we have to do is to make the constant the subject of the formula. Then we obtain the units and dimensions of the quantities that are involved in the equation. Now, sometimes we might just need to solve for the unit, or we might need to solve for the dimension, or we have to solve for the unit and dimension. So that depends. So the step 2 depends on the one we are solving for, either unit or dimensions of the two, or the two rather. Then after we have obtained the units and dimensions of the quantities involved, we have to substitute them into the new equation that we have derived in step 1. Then we perform basic arithmetic operation. The arithmetic operation we are talking about is the indices, the one that involve indices, so that we can get our required or desired answer about the constant. So let's take a look at a few examples on this. Yeah, so here we are. Let's try to solve this question. As you can see, find the dimensions and units of K so that the equation V equals to K times density is dimensionally correct, where V is velocity of sound and rho is the density. We are going to be using these 4 steps to solve the question. Let's write our equation. The equation says V is equals to K times density. Equation 1. Step 1 says that we should make our constant the subject of the formula. So let's make the K the same formula. That means we will divide through by density. So K is going to be equals to velocity over density. That's equation 1. The step 2 says that obtain the units and dimensions of the quantities involved. And I told you that this part depends on what the questions say we should do. If questions only required dimension, there is no need for us to get the unit. But the question says we should solve for unit, there is no need for us to solve for dimension. But in this example 1, the question says that we should solve for unit and the dimension. So we can start with dimension or we start with unit. Let's make in step 2. Let me write step 2 beside it. Step 2 says that we should solve for the unit and dimension. The unit, let me start with unit, A part of the question. What is the unit for the quantities involved? We have velocity and density. The unit for velocity is meter per second, while the unit for density is kilogram per meter cube. How do we obtain kilogram per meter cube? Let's quickly work things out here. As we can see that density is mass over volume. Now, what is the unit for mass? That is kilogram, and the unit for volume is meter cube. We try to simplify this to be having kilogram per meter cube. That's the density unit as density unit. So we have this. Then now that we have gotten the units of the quantities involved, let's substitute by, which is step 3. Substitute back to equation 2. That's the new equation. That means that's step 3. Equation 3. So we are going to be having K is equals to velocity rather is meter per seconds over density, which is kilogram per meter cube. So if you try to simplify this, we are going to be having the unit of the constant K to be, we have only 1 kilogram, which is at the denominator side. It goes up, becomes per kilogram. Then we have 2 meter. We can solve this using indices to get, if you solve it using indices, that's to say we have meter raised power 1 divided by meter raised power minus 3. That will give us, we pick one of the base, the first power is 1, division means minus, then the second power is minus 3, and that will give us m raised power 1 minus times minus give us plus. We have 3, so we'll be left with m raised power 4. So if I solve for the m that we have here, we are going to be having m raised power 4. Then we have just one s, which is s raised power minus 1. So this constant, its dimension is per kilogram, meter raised power 4, s raised power minus 1. Let's obtain the dimension as well. Dimension of the constant involved. What's going to be the dimension of this constant? Now, to work out the dimension, what is dimension of velocity? Say dimension of velocity is Lt raised power minus 1, while the dimension of density rho is equals to ml raised power minus 3. How do we obtain ml raised power minus 3? We can still use the formula for density. Density is mass over volume. Then the dimension of density is going to be, dimension of mass is m, while the dimension of volume is L raised power 3. So in that case, we have obtained the dimension of density to be equals to m L raised power minus 3. So that's how we obtain the dimension of density to be this. Now that I've obtained the dimension of the quantities velocity and density, we can substitute back into equation, the new equation, which is the third step that we have discussed. That means the dimension of the constant k is going to be equals to velocity, which when we look at it, velocity in the new equation, velocity is at the numerator side. That will give us Lt raised power minus 1 over density is ml raised power minus 3. Now, how do we solve this? We are going to perform basic arithmetic operation which involve indices. We have a single m, goes up, becomes m raised power minus 1. We have just one t, but we have 2l. We can solve it as well using indices. We solve it using indices. We have l raised power minus l raised power 4, then t raised power minus 1. Since the t is at the numerator side, it's not changing its position. So this is the dimension for the constant. Now let's look at another example. So in the second example, as you can see on the screen, derive the dimension as units of the constant in Newton's law of gravitation. Feel free to pause the video so as to try it. First thing is, what is the expression for Newton's law of gravitation? It says that gravitational force of attraction is equals to G m1 m2 over r square. That is it. So now they said we should solve for the dimension and unit. Before that, the first step we are to take is to make the constant involved the subject of the formula. The constant involved here is G, as the gravitational constant. Let's make it the same formula by cross multiplying, and we have fr square is equals to G m1 m2. Now on the part of G, right hand side, m1 and m2, they are attached to G. So to remove them, we have to divide both sides by m1 m2. Divide both sides by m1 m2. The value for G is going to be equals to G equals to fr square over m1 m2. That's the new equation. Now let's get the unit and the dimension. Let's say we want to solve for the dimension first. To solve for the dimension, the quantities involved are 3. We have force, distance, and we have the masses. Now What is the dimension of force? We have discussed that it is mlt raised power minus 2. Dimension of distance is L. The dimension of the masses M1 is capital letter M, and dimension of the second mass M2 is also capital letter M. So now that I've gotten the dimensions involved, then we can return them back into equation 2 by substituting. So G dimension, gravitational constant, is going to be equals to the dimension of force is ml square, mlt raised power minus 2. Then dimension of distance is L square over dimension of the first mass is M, second mass is also M. Now let's try to simplify it using indices, which is the last step. Perform basic arithmetic operation. Means this M, we cancel one of the M, so we'll be left with what? M. M is a denominator, so it becomes M raised power minus 1. Now we have two L involved, L and L squared, that gives us L raised power 3. Then we have T raised power minus 2 alone. Then we have this as the dimension of gravitational constant. Let's work out the unit as well. The units for the gravitational constant, the unit for force is Newton. We are working with the derived unit. You can as well work with the basic unit. The unit for radius, which is the distance, is meter, and the unit for the first mass is kilogram, while the unit for the second mass is also in kilogram. Now that I've gotten the units of the quantities involved, let's return it back into the new equation, which is equation 2. And equation 2 says G is equals to FR square over M1 M2. That means let's substitute our value. Force is Newton. Our distance is meter, but we have square of it. Then over the first mass is in kilogram, while the second mass is also in kilogram. So if we multiply it, we have Newton meter square over kilogram multiplied by kilogram, that gives us kilogram square. So the kilogram square is at the denominator, so when it is going up, becomes negative. Kilogram raised power minus 2. Then we have Newton, then we have meter square. But it is more appropriate to write positive numbers before negative number. So in that case, we are going to be writing it as Newton meter square per kilogram square. That is the units and dimension of gravitational constant. So we can use dimensional analysis to get units and dimensions of some constant, provided that they have dimension. And the principle behind this is principle of dimensional homogeneity. Provided that the right hand side is equals to the left hand side, we can confirm that the left hand side equals to the right hand side for Newton's law of gravitation, to show that Newton's law of gravitation follows principle of dimensional homogeneity. How can we do that? Let's take a look at it. From F is equals to G M1 M2 over R square. Let's try to check maybe the left hand side, which is force side, is equals to the right hand side, which contains all these parameters. Now I can use base unit method, and I can as well use dimension method. Let's say we want to use a dimension method, or let's use dimension method to solve this. That means we are going to be obtaining dimension of force to be ml square, mlt raised power minus 2. Then dimension of gravitational constant, since we have derived it, it is given as m raised power minus 1, as m raised power minus 1 L cubed t raised power minus 2. Then for the distance, its own dimension is L. Now that we have gotten dimensions, we can return it back into equation 1 by saying F, in place of F, write ml t raised power minus 2, equals to gravitational constant is m raised power minus 1 L raised power 3 t raised power minus 2. multiplied by our first mass is m, then second mass is also m, over the distance is L squared. So let's try to simplify this bunch of parameters we are seeing here. We can start with anyone. Let me change the ink. So here we have 2m that give us m L t raised power minus 2 is equals to m raised power minus 1, as m times m will give us m squared. Then we have, this is 3L, this is 2L to cancel out. Then I'll be left with 1L here on the other side. We're having t raised power minus 2. Now, let's simplify these two, m raised power minus 1 and m raised power 2. We can apply indices. Since they're having the same thing, we'll pick one of the m. So the first power is minus 1, while the second power is 2. By using indices, and that will give us m raised power minus m raised power 1, m raised power 1. So in that case, the left hand side is mt raised power minus 2, while the left hand side is mt raised power minus 2, while the right hand side is since we have simplified this, we are obtaining m raised power 1, then we have lt raised power minus 2. As you can see that the right hand side is equals to the left hand side. That means that Newton's law of gravitation is dimensionally consistent and is dimensionally correct. Therefore, principle of dimensional homogeneity is valid for Newton's law of gravitation. Let's look at the last application of dimensional analysis, which is talking about establishment of an equation. We can use dimensional analysis to establish equations as well, and this depends on number of other physical quantities. The knowledge of indices and the principle of dimensional consistency is usually useful when deriving an equation. For example, happiness depends on money and food. If you are to put this in mathematical form, it means H, let's say H represents happiness, depends on money and food. So after writing it in mathematical form, the next thing is to remove the proportional sign and introduce a constant. So writing it as H equals to K, and I write NF. The next thing is to give the independent variables power. What are the independent variables? The independent variables are mostly the variables that are always on the right hand side, for example, mass and food, while the dependent variable is always on the left hand side. That means happiness is a dependent variable and it is depending on money and good food. So the next thing is to give the independent variables powers, as I've said earlier on. That means we'll be writing H is equals to K, then you write M. You can give it powers in terms of A, B, C, can give powers in terms of X, Y, Z, or P, Q, R. Now, B. After giving the independent variables power, I can say this one represents equation 1. Then the next thing is to obtain the unit, if I'm using unit method, or obtain the dimensions of both the dependent and the independent variables. So to solve this, is either we make use of base unit method or we use dimension method. Some questions will surely specify which method to be used. Then in this case, we are going to be solving for the powers, the values of the powers. After obtaining the values of the power, then we return it back into this equation and understand how happiness depends on money and good food. So let's take a look at realistic example under this application. Yes, so let's take a look at the example that we are seeing on the screen. They say that the velocity v of a streamline flow depends on the radius r of the two, density d, and coefficient of viscosity. So that's you're supposed to have a coefficient of viscosity. So how are we going to solve this? They said use the method of dimension to obtain expression for v. To solve this, the first thing is to translate this question into mathematical form. Like I've told you, we are going to be writing it as the velocity depends on, say that as v, v depends on said radius. It also depends on density and coefficient of viscosity. That's the first thing. Now, the next thing is to remove the proportional sign so that we can introduce a constant, right? As v is equals to k, we have radius, density, and coefficient of viscosity. Now, we have gotten this is to write it in terms of powers, give the independent variables power. We have three independent variables here. We have radius, we have density, then we have coefficient of viscosity, while velocity is the dependent variable. So how we're going to do this is to give them power by saying v is equals to k. There's a constant, so we will not give it power. That is r raised power x, density raised power y, then coefficient of viscosity raised power z. That will be our equation 1. Then they said we should use dimension method. So that means we have to obtain the dimension of the parameters involved. Dimension of velocity is Lt raised power minus 1, and the dimension of distance, which is our radius, is L. The dimension of density, we have discussed that is ml raised power minus 3, and the dimension of coefficient of viscosity, that is ml raised power minus 1, c raised power minus 1. How do we get that? We use this principle, we use the formula that says coefficient of viscosity is Fl over AV. So in that case, we are going to be having force is mlt raised power minus 2 multiplied by distance L over, we have area is L square, while velocity is Lt raised power minus 1. So if we try to solve this, we are going to be having it to be ml minus 1 c raised power minus 1. I'll go about that. So now the next thing is, since we have gotten the dimensions of the independent variables, let's substitute it into equation 1. That means we are going to be writing it as, in place of velocity, write Lt raised power minus 1, because we ignore the constant for now. Then we have radius is L, the power there is x, that density is ml raised power minus 3, its own power is y coefficient of viscosity, is m raised power minus 1 c raised power minus 1 of z. Now we can open the brackets by using indices as well. Give us Lt raised power minus 1 is equals to Lx m raised power y, L raised power minus 3y. Then if I open this one, I'll be having m raised power z, L raised power minus z, c raised power minus z. Now let's rearrange this in terms of MLT for simplicity's sake. I mean, you should be writing Lt raised power minus 1 is equals to, let me write m first, that gives us m raised power y, then m raised power z will follow, then L raised power x, L raised power minus 3y, then we have L raised power minus z. But we only have one t on this side, which is this, so write t raised power minus z. If that be the case, we can apply law of indices to simplify this as well, to give us m raised power y plus z L raised power x, we are adding the powers together for L. Since they're having the same base, we are adding the powers. That is x plus minus 3y will give us minus 3y minus z. Then we have t raised power minus z. So if you consider the right hand side and the left hand side, we have MLT on the right hand side, that is MLT dimension, but on the left hand side we have L and T. So how we're going to do it is to try to manipulate in such a way that it doesn't disturb the original equation. Since there is no M on the left hand side, we can introduce it by writing it in this format, m raised power 0, because m raised power 0 will still give us 1, to give us this one back. Then we are having LT raised power minus 1 is equals to m raised power y plus z, L raised power x minus 3y minus z. Then we'll be having t raised power minus z. So what are we going to do now is to apply the principle of dimensional homogeneity. What this principle says that if an equation is dimensionally correct, that means the left hand side is equals to the right hand side. So in that case, let's compare the terms on both sides. Compare m. Let's compare m on both sides. M on the left hand side is m raised power 0, while the m on the right hand side is m raised power y plus z. In that case, m can cancel m. If m cancels m, that means, why do we cancel it? Because they have the same base. According to the law of indices, that means we are going to be left with y plus z is equals to 0. Let's make that equation 2. Since we already have equation 1 from the start, then let's compare the next term, which is L. L on the, as you can see, L on the left hand side is raised power 1. That's it here. So we have L on the right hand side, while the L on the right hand side is raised power x minus 3y minus z. So we can cancel both sides as well. That will give us, to also give us, that is x minus 3y minus z is equals to 1, equation 3. Then the last one is comparing t on both sides. So if you try to compare t on both sides of the equation, the t on the, as you can see, the t on the left hand side is t raised power minus 1, while the t on the right hand side is t raised power minus z. So in this case, the t will also cancel out, then because of the fact that they have same base, then we are going to be left with minus z is equals to minus 1, and that our z is going to be equals to 1, since in this case minus cancel minus, or divide both sides by minus 1. So we have gotten the value for z. We can substitute into equation 2 so as to get value for y. Equation 2 says that y plus z is equal to 0. So if that be the case, we are going to be having equation as y plus z is 1 is equals to 0. Then the equation becomes, we take 1 to the other side, becomes minus 1. We have also gotten the value for y. Let's get the value for z by substituting y and z into equation 3. In equation 3, we have x minus 3y minus z is equals to 1. That's equation 3. This one is equation 2. Let's substitute the value. That means we have x minus, the value for y is minus 1. Then the value for z is 1 is equals to 1. So we are going to be having x minus 3 minus 1. If we multiply that, give us plus 3 minus 1 is equals to 1. So that gives us x. 3 minus 1 gives us 2 is equals to 1. Then we can take the 2 to the other side by writing it as x is equals to 1 minus 2, and our final answer becomes minus 1. So since we have gotten the value for x, we can just conclude that the value for x is 1, while the value for y is minus 1. The value for y is also minus 1, and the value for z is 1. That is our parameter we have got. Now that I've gotten the values, the powers for the independent variables, we can return them back into the original equation that we have. As the original equation that we have says that v is equals to k r raised power a, density. We have density there. Yes, we have density raised power y. Density raised power y. Then we have coefficient of viscosity raised power z. So that's equation 2. Then let's substitute our value back. So we are going to be having v is equals to k. Our value for, it's not a, is x. Our value for x is minus 1. Density is minus 1. That's value for y. Then our value for coefficient of viscosity is 1. So after getting this, the next thing is to simplify this. How do we simplify this? V is equals to k. This one is inverse. When it goes down, becomes 1 over r multiplied by 1 over density. And this one is still at the numerator side. So we try to multiply it. Our velocity equation is going to be equals to k coefficient of viscosity over rd. And here we are able to derive an equation for velocity. We have derived an equation for velocity. So let's look at another example to buttress establishment of an equation. So let's look at the second example. They said the speed of sound v in a medium depends on its density, on its wavelength lambda, the Young's modulus E, and the density rho of the medium. Use the method of base units to derive a formula for the speed of sound v in the medium. Now, the first thing we have to do is to transform the statement into mathematical expression. How do we do that? They said the speed of sound v, as you can see, the speed of sound v depends on the wavelength. It's also said it depends on the Young's modulus. At the same time, depends on the density. If that be the case, the next thing is to transform this equation by removing the proportional sign. So we're having v is equals to k density. The wavelength, Young's modulus, and density. Now, after removing proportional sign, let's give the independent variables power. The independent variables are wavelength, Young's modulus, and density, while the dependent variable is velocity. So let's give them powers. We are going to be having v is equals to k. We have wavelength raised power a, then Young's modulus raised power b, density raised power c. Then we can make that as equation 1. The next thing now is to follow the condition of the question. The condition given here is that we should use method of base unit to solve it. So we are going to use method of base unit. That means we are going to obtain the unit for velocity, wavelength, Young's modulus, and density. The unit for velocity is meter per seconds. What is unit for wavelength? That's length of the wave. It is also in meter. And the unit for Young's modulus, we can as well work it out as it is also. Let's try to see Young's modulus is having the same unit as pressure. So we can work it out by using Young's modulus equals to stress over strain, of which stress is having force over area. So if we work for stress, that is, the unit for force is kilogram meter per second square, area is meter square. So if I try to work out the unit for stress, I'll be having kilogram per meter per second square. Now let's try to work out the unit of strain. Strain unit is extension over length, and the unit for extension is meter, while the unit for length is meter as well. In that case, they can both cancel out to give us 1. If that be the case, we can return back to this original expression that we have here to get the unit for stress, I mean the unit for Young's modulus, and that we are going to be having Young's modulus to be equals to stress is kilogram per meter per second square, while that of strain is 1. Since it is dimensionless, we are going to be having kilogram per meter per second square as the unit for Young's modulus. So we can go back to make use of it by writing kilogram per meter per second square as the unit. Then we need units of density as well. The unit for density is kilogram per meter cube. That be the case, since we have gotten the units of the parameters or the variables involved, let's return back into equation 1. That means in place of velocity, we are going to be writing meter per second. We ignore the constant k. Now wavelength is a meter, and that's raised power a. Our Young's modulus is kilogram per meter per second square, and its own power is raised power b, while density is kilogram per meter cube, and that is equals to c raised power c rather. Then let's open the brackets by using indices. We are having meter per second is equals to meter raised power a. Open brackets, we are going to be obtaining kilogram raised power b, meter raised power minus b, s raised power minus 2b. Then this one will give us kilogram raised power c, meter raised power minus 3c. Let's try to rearrange them. On the right hand side, meter per second is going to give us, let me write kilogram first, that give us kilogram raised power b, kilogram raised power c. Then we have meter raised power a, meter raised power minus b, and meter raised power minus 3c, and we are left with s raised power minus 2b. So now we can simplify it. Let's try to simplify it by working with indices as well. Meter per second becomes kilogram, pick one. We'll be having b plus c. Then we have m. We have pick one of the meter. We have the first power is a minus b minus 3c. We have s raised power minus 2b. So if you look at the left hand side compared to the right hand side, there's no kilogram on the left hand side, so we have to introduce it by ourselves by raising its power of 0. Then we have meter per second, so we have in kilogram raised power b plus c. Then we have meter raised power a minus b minus 3c. We have s raised power minus 2b. Now we can apply the principle of dimensional homogeneity, whereby the left hand side is equals to the right hand side. By comparing the kilogram on both sides, let's compare kilogram on both sides. By comparing kilogram on both sides, we are going to obtain kilogram raised power 0 is equals to kilogram raised power b plus c. In that case, kilogram will cancel kilogram. We'll be left with b plus c is equals to 0. Equation 2. Let's compare the meter on both sides as well. Let's compare meter on both sides as well. So comparing the meter, as is to say, meter on both sides. The meter on the right hand, on the left hand side is meter raised power 1. On the right hand side, we have meter raised power a minus b minus 3c. So if you try to cancel out meter, cancel meter, because they're having the same base, then we are going to be left with a minus b minus 3c is equals to 1. Equation 3. The last one is to compare the seconds term. Let's compare seconds as well on both sides. The seconds on the left hand side is raised power minus 1, while the seconds on the right hand side is raised power minus 2b. So if we try to cancel it out, we are going to be left with minus 2b is equals to minus 1. So we can get the value for b by dividing both sides by minus 2b. Minus 2 rather, minus 2. So we have minus 2 cancel minus 2, minus cancel minus. Then the value for b is going to be equals to 1 over 2. We have gotten the value for b. We can substitute the value for b into equation 2 so as to get the value for c that we have in equation 2. So let's try to substitute. That means b plus c will give us 0. That's what we have in equation 2. So in that case, we have b is 1 over 2 plus c is equals to 0. Takes 1 over 2 to the other side to get value for c. That will give us minus 1 over 2. Now we have gotten the value for b and c. We can substitute the 2 into equation 3 so as to get the value for a into equation 3. Equation 3 says a minus b minus 3c is equals to 1. Substitute our value. Substitute our value here. That means a minus, in place of b, we write 1 over 2 minus 3. In place of c, we write minus 1 over 2 equals to 1. So in that case, we are going to obtain a minus 1 over 2 minus times minus will give us plus 3 over 2 is equals to 1. So when we try to simplify this, our value for a becomes, so we obtain 0. In short, our powers, we have 0. Then for b, we have 1 over 2. And c, we have minus 1 over 2. Since we have gotten the powers involved, now we can substitute it into the original equation that we have transformed. The original equation says that we have v is equals to k a wavelength raised power a, Young's modulus raised power b, then density raised power c. That's equation 2. Then we are going to have v equals to k. Our Young's modulus, our wavelength, which its own power is a, is 0. Then the Young's modulus b is 1 over 2, while the density, its own power is minus 1 over 2. So when we try to simplify this, we are going to have v equals to k. Wavelength raised power 0 will give us 1. We are left with e raised power, v equals to k. Then we have E raised power 1 over 2, then density raised power minus 1 over 2. So we have V equals to K. In this case, we have E raised power 1 over 2, then density goes down, we have 1 over density raised power 1 over 2. So how we're going to do this is to write it in form of square root. That gives us V equals to square root of E over square root of density. See, we apply the law of sort that says since they're both having square root like this, we are having square root of A over square root of B. That will give us square root of A over B. So when we try to apply this in solving this question, we are going to have our equations to be V equals to K square root of E over density. Now, some cases they will give us the value for K, some cases they will not give us the value for K, the value for the constant. That means if you are not giving the value for constant, maybe it is an equation that we are familiar with. For example, in the case of period of a simple pendulum, let's say we have solved for it and we are having T equals to K square root of L over G. In this case, they assume that we should know the value for K because K in simple pendulum is 2 pi. Sometimes they will give us, sometimes they will not give us, but in this case, it will be taken as 1, then V is equals to square root of E over density. That is the equation that we have derived for the question, for the example 2 above. Thank you.